Okay, let's get started. So we've covered a lot on latency, and there's more works. I think this is a fascinating area. We should rethink the systems in terms of how we think about latencies today. But I'm going to stop the latency at this and summarize what we've covered. Basically, we looked at two major reasons for latency, long latencies in existing memory systems. One is the design of the DRAM microarchitecture, and the second is this one-size-fits-all approach to latency. And we try to break both of those mindsets. I think both of these are dictated by the mindset today. Once we actually change our mindset, it's a lot easier to find techniques that can buy us relatively low latency at hopefully low cost. And initially, maybe we find techniques that are high cost, but over time, we can reduce the cost of those techniques. And that's how progress happens. And if your reviews tell you that you don't need low latency, you don't need better random number generators, don't believe them. I think some people know better. Okay. So I'll talk a little bit about DRAM power consumption. I think this is interesting. There's also more work that needs to be done in this area. And we've done some very recent work that I'm going to very briefly go over in terms of measuring real power consumption. This is an area that's very interesting because we were always trying to evaluate, what is the power consumption of the method that we develop? And we always relied on power models that were developed in the past, which are usually based on either some sort of circuit level simulation or datasheet values. DRAM manufacturers publish these datasheet values where they actually say, this is the current drawn by this activity, for example, a refresh. This is the current drawn if you actually do an activate. This is the current for a read. So they have these 9 or 10 different current values that are in the data sheets. And the question always is, like, how reliable are those values, right? It's written in those data sheets, but how reliable are they? And that's exactly what we tried to answer. So we extend our infrastructure with this fancy stuff, with the power measurement platform more recently. So we can measure the power. Of course, you need to do a lot of tricks to actually really understand where the power goes. But we can do that, and you can read the paper with that. So that's our FPGA. That's not shown. And we need to use the riser board. So we actually failed to do this in many ways, and then finally we got it to work to do the power measurements in a reliable way. Okay, I'm not going to go through this. So basically, we extended the infrastructure, and we tested about 50 DDR3L DRAM modules. We still cannot test in this infrastructure LPDDR4. And we tested modules from 3 major vendors manufactured between these years. And we did a bunch of experimental tests, basically, to see how power is consumed in current DRAM. So basically, the first question is, how reliable are the datasheet values that the manufacturers provide you in DRAM? And the answer is they're not reliable. There's a huge variation from the datasheet values. So this is basically the first conclusions over here. These are some of the IDD. These are called the IDD measurements, basically power current measurements. And the datasheet value says for manufacturer A, for example, the current idle current, when the DRAM is idle, this is supposed to be the current. But what we measure is much lower than that, actually. And there's some variation across the chips. And that's true for all manufacturers. Sometimes it's much lower, sometimes it's much higher. But there's clearly a margin in terms of the IDD values that the manufacturers provide, just like in the latency, right? So this is as expected because manufacturers are very conservative in terms of their specifications. This is another current activate precharge, IDD 0, and that's very similar. And this is the read value. And this corrected thing is we need to actually correct some things because we cannot perfectly get the values in our measurements. But basically, different vendors have very different margins. There's low variance among different modules from the same vendor, actually. As you can see, the variance is very low from the same vendor. Yeah. And current consumed by real DRAM modules vary significantly. Yes? So we're going to get to that. Conclusion number 4 is going to validate exactly what you said. Here, there's a lot of margin, but let's see what happens across generations. Okay, so the second thing, which should not surprise you, I think, based on what we've discussed so far, is DRAM power is very much dependent on data values. This is the number of ones in a cache line, and this is the read current.
They try to give you like many
Yeah, that's what.
They have to commit for that.
Yeah, exactly. Mm-hmm.
Usually people will not complain if it's lower, especially when you talk about cars.
That's right, yes. I think so, actually. I think so. But, I mean, it's not clear if we are able to measure the worst case in our infrastructure at this point.
Also, unlike latency when data is on latency and you slow down your phone, you actually pain.
Yeah, that's right.
Current, if they don't take the current, you're not spending the power, so no damage done.
That's right, yes.
Very well.
Yeah, I mean, it makes sense, I think, from that perspective, except there's a huge margin, as we can see, right? Okay, so data values, if you want to learn more about this, there's more in the paper, but you can see that there's a clear correlation between the data pattern and the read current and the write current. And there's a lot of analysis in the paper. Some of it is intuitive, some of it is not so intuitive, but take a look at it. I'm not going to talk about this a lot more here. But DRAM power consumption depends strongly on the data value that you're reading or writing. Okay, structural variation is also present here. Basically, you get different power draw across different banks, for example, in some cases. It's not as visible for vendor N and vendor B in terms of the idle current across banks over here, but in vendor C, there's a lot of variation across banks in terms of the idle current. And in terms of read current, there's a lot of variation. A lot depends on what you specified, but this is within like 7% or so here, but there's a lot more over here. And there's a lot more data over here. And there's a big variation in activation based on the row address. So some row addresses draw more current, depend on the number of ones in the address, which is also really interesting, and there's more analysis in the paper. Some of these we don't fully understand at this point, but this is the data that from real chips. Okay, basically DRAM power varies systematically by bank and row as well as we can see. So this is maybe the number 4. This is what we found, which we were actually a bit surprised. Generational savings over time, over manufacturing years, are actually smaller than expected. If you look at the data sheets, you'll get a much larger value, but the measured values are actually much smaller, according to what we see. So maybe DRAM manufacturers boast a lot about reducing the power, but we don't observe this, at least in our measured systems, because worst case maybe reduces, sure, but the average case that we look at, or the common case temperature that we look at, doesn't reduce as much. Okay, and we see similar trends. These are the currents for activate, pre-charge, and write, but there are similar trends for idle and read currents. Yeah, that's the other conclusion. I think this is interesting. Okay, these were the observations, and there are more observations in the paper that I'm not going to go into.
You talked with any of them about that? Or?
Yeah, we talked with some of them, yes.
What did they say?
They listen.
In a way, they listen. If you go back for a minute,
With this one?
These are the years. So they were, in time, they seem to be more.
I mean, it's reducing.
Closer to the gap is reducing.
Yeah, that's right, that's right.
In a way, they listen. It's not to you, maybe, but.
So basically, what the data sheets show are not what we see, but there's the trend is the same for sure, but the delta is much smaller in terms of what we observe. And we see an increase over here, so that also exists. We don't know exactly why. Yeah, I mean, it's good to talk more, certainly, with manufacturers. So we have channels, but we don't necessarily understand, and they're not always forthcoming in providing all the information clearly, right? Okay, so based on this, actually, we provide a new power model. This is also open source. This should go live, actually, maybe today or yesterday. We call it the Vampire. I like this name. So basically, what this power model does is you get inputs from a memory system simulator, the trace of DRAM commands and timing, and data that's being written, because data is very important. And you feed it into the model, and model does read, write, and data-dependent power modeling, and idle, activate, pre-charge power modeling based on the experiments that we've done, and structural variation-aware power modeling also. And the outputs are per vendor power consumption and range for each vendor optionally. So previous power models actually had none of these. This is a more accurate power model according to what we measure. And this is hopefully already open source, but if not, it will be open source very soon. And this is we validated this, well, details in the paper is gone over here, but we validated this compared to other models also. This is the absolute percentage error. This is the micron model that a lot of people use. Basically, all of these are somehow data sheet based, and they do some fudging. And this is the DRAM power that we used previously. So there's significant error that you get in previous models, and the error that we have in our model is relatively small. Of course, we can improve it better going forward. Okay, so that's the idea. So what can you do? What can you do with these models? Certainly, you get better accuracy, but in the paper, we also look at some other things. So for example, you could take advantage of the structural variation to perform variation-aware physical page allocation to reduce power, because there's a lot of variation in terms of banks, in terms of their power draw. That could be interesting. You can do more intelligent power down scheduling in DRAM. We didn't look at it in detail. We did one thing. We looked at reducing DRAM energy with data dependency-aware cache line encoding. So some encodings clearly consume less power. Some encodings consume more power. And we developed an optimized encoding based on what we observed. And if you actually do that, you can reduce the power, in this case, DRAM energy over time by about 12% compared to the baseline. And these are different encodings that we examined. You can look at the paper for more detail. I think there could be more work done. This was just a case study to show what you can do with the observations that you develop from a real system and using the power model that we develop also. Hopefully this could enable other studies as well. And this is the paper. This was published very recently at Sigmetrics. Okay. Any questions? I wanted to sneak in power here also. Yes.
What do you mean by encoding? What is 0, what
Exactly. What is 0, what is 1, basically.
With the cache line, you always have more zeros than ones.
Exactly. That's one encoding. Exactly. Yeah.
In the encoding, do you take into account the overhead?
Overhead of conversion.
For example, that's one thing, but also the overhead of representing. For example, flip or not flip.
Yes.
You need one extra bit.
Exactly. Yeah, yeah. Basically, metadata overhead. Yeah, yeah. We did take into account the metadata overhead. Sure. Okay. So we've been covering this. We've covered the low latency portion. I'll derive some solution principles. I think this is general across everything we discussed so far. It's maybe more or less applicable to some things. But I think one of the things that we've discussed is data-centric system design and intelligence spread around. I think that's important. Do not center everything around traditional computation units. I think the things that we are discovering right now with DRAM, maybe if we didn't have the processor-centric view, maybe would have been mainstream by now, right? That's debatable, of course, but we've been so focused on processor and so optimized it that we maybe ignored the other parts of the system. And I think today we talked about this also, better cooperation across layers of the system, careful co-design of components and layers, system architecture and device, and having better, richer, more expressive and flexible interfaces. Like we discussed, exposing portions of the DRAM device to the memory controller, that requires better cooperation across different layers and components, clearly. I think these are very fundamental principles to achieve a better system. Better than worst case design. Today we've talked a lot about that. Basically, we are optimizing for the worst case in latency and maybe also power. We still need to understand that. And maybe also voltage, right? And worst case is really determining the common case operation. But maybe we should really revisit that. We've been doing that a lot in the, again, processor design space, but we need to do more in the memory design space also. And the last one is obvious. We've discussed this a lot, heterogeneity in design and exploiting underlying heterogeneity as well. I believe this enables a more efficient design. There's no one-size-fits-all. And not everything is the same also. So if you exploit these principles, I think we can have a better system. And I think I've given examples of exploiting these principles in different ways over the last 2.5 days or so. I think more compact. Yeah, I think this is, I added some other things over here like flexibility and adaptability. I think those are important. Okay. I'll conclude very similar way to yesterday. Basically, we need some principled system architectures to solve the memory problem. And this is what I said yesterday. But I think this is what I didn't say, maybe making memory a key priority in system design and optimizing it and integrating it better into the system. So far, from a far-away perspective, memory was not as big of a priority in system design. As a result, as I said just now, like we're discovering these things. better and better. But it's because it was not a key priority. But if you make it a key priority, maybe we can optimize it and integrate it much better into the system. And this is similar to what we've discussed yesterday. It's going to lead to many improvements that we haven't thought about before. But I think a lot of these require some rethinking. Maybe some of the things that I discussed today don't require a lot of rethinking of the algorithms, of course. Okay, so that's the end of low latency. Any questions, thoughts? So I'm going to switch gears to another lecture. This is your opportunity to delay switching. No? Okay, let's see what's the next lecture.